Hey all, how's it going? So in this video, I wanted to just show you that I found a new ensemble method that we can use rather than we were using gradient boosting regressor before, which is another tree-based algorithm. And through some trial and error, by trial and error, just meaning that I tried out a couple different algorithms, I found this extra trees algorithm to be slightly better. It improved the testing accuracy by about 9.5%. So it's a little bit better. It's not like night and day, but I just wanted to show off how I do that. So let's get into it. All right, so the first thing that we're going to want to do is this also comes from sci-kit learn, the ensemble that we have here. So just import that. All right, next we're going to come down here to the parameter grid. So we're still going to use grid search CV as we were since the last video. But this new parameter grid, so I'll paste it in here. So the first thing to notice is that we don't have learning rate anymore, and that's due to the nature of the algorithm or ensemble method that we're choosing from sci-kit. We don't actually have a learning rate, and that's because gradient booster was more of a sequential tree algorithm, so it would update the learning rate each time. Which this is more of a tree-based algorithm where we have a bunch of random trees. So we don't actually have learning rate anymore. The next thing to notice here in the parameter grid is that we have this min samples split and min samples leaf. And these ones take a little bit of explanation. It took me a little while to, I think, I kind of figured it out, so I'll do my best here. So I had Claude go ahead and whip up for me kind of like a visual example, and I played with it a little bit to get this little image here to kind of visually represent what's going on. So this is the tree that you're going to see. So it's going to start at we're going to say that root samples split is 10 and root samples leave is 5. And so what those mean is for every node, we have to have at least 10 samples to split. And then every leaf that we make, a leaf node just has no descendants, has to have at least 5 to split. And if that leaf node can't be created, then we're just going to call the parent a leaf node and just kind of quit out there. A way to think of that is we can start with 57 samples, right? So that's greater than 10 samples. So we can split that, right? So we split it to 38 and 19. Both of those are also over 10, so we're going to attempt to split those. And node A, that worked successfully. We split that into 25 and 13. That's fine. And then node B, the algorithm will split it into, these are its candidate splits, which I'll explain in a second. So these are 3 samples and 16 samples. 3 is below 5, so it can't be made into a leaf. And because of that, the entire split is not going to work. So instead, node B is just going to be created as a leaf node, and it's going to have no descendants. So then over on this side with node A, 25 can be split into 18 and 7. 7 can't be split any further. That's fine to just stay as a leaf since it's greater than 5. And then the 18 will also leave as 5. The right node for node A is 13, and it attempts to split it into 4 and 9. 4 can't work, so the entire node A right side descendant is going to be created as a leaf node. Now, as for the candidate splits that I mentioned, so that is based on the way that the algorithm forms these splits. So you can't, in practice, you can't think of it like an arbitrary number like this. Well, I mean, you can for this visual example, but it's not going to just, the algorithm doesn't just try arbitrary splits like that. It has actual logic as to the samples that are being determined. So when it tried to split 19 into 3 and 16, you might just think, well, why doesn't it just try to do something like 5 and 14 or something like that? And that is just the nature of the way that the algorithm formed the split. And that's why I wanted to kind of leave this one in here, because it kind of explains that a little bit. So coming back to the code, we do have those two new parameters. N estimators and max depth are the same. They're not the same values as we had before, but we also had those parameters as well. And N estimators is just the number of trees that we're actually trying. And the max depth is just the depth of the tree, so how many actual nodes. Now we're going to change the actual model itself. So we're not going to use gradient boosting regressor anymore, and we're just going to take in this print statement, since this was just to show you the values that we are trying, which I want to show some other stuff. Similarly, we can remove showing all the R2 scores, as we just want to show the last ones now. Now, what I do want to show here is I do want to show the previous model settings that we have. So the previous optimized model settings that we got from the last video here. So if we paste that in, we found that the best parameters were N estimators 50, learning rate 0.05, max depth 3, and random state and verbose. Those are just, you don't really need to pay attention to those. Random state is just so it's replicable, and verbose just so that we can see some stuff going on. So then we do the model fit, we get the scores on there, and then I just have some print statements here so that we can see the feature importances that we had previously compared with what it will be now, as well as what our previous training and test scores were. Okay, so now, provided I copy and pasted everything correctly, we can just run make train from the command line. And so it has more candidates now because it has more features in the param grid. So these R2 scores down here are kind of the important things to pay attention to. So the test R2 score, remember, that's like how our model is performing on unseen data, has improved. It did go from 0.34 something to 0.37 something. So it did get that 9.5% improvement on the testing score. What's also important to notice too is our training is at 0.63, which is also higher. That's not always the best thing though. 0.63 it's still pretty reasonable. If we get something like 0.95 or something like that, and then our testing score is still like this, which is still kind of a poor performance, then that's not good, because that means that the model has just kind of memorized the training examples that we have. So it's performed very well on that, and it can't perform on test data. Remember, that's called overfitting, and that's something that we want to avoid. I did also want to point out, we probably could have taken this print statement out too, since that's not really all that important anymore. The feature importance changed too. So now we have run 400 as the top contributor of importances, which makes sense. The run 400 is going to be the best predictor of how you can do in a 5K. And then we have Helen up there, which I think we had before. What's interesting is, so if you compare this with baseline, gender had nothing to actually do with how you were performing. And now that's moved up to the third highest contributor. So that's age, which is something that in the gradient booster only contributed 0.3%. And that's arguably a very big contributor, has moved up. It's moved up a little bit. It's still not as high as would intuitively make sense. And part of that, as I said before, is kind of the constraints of the data that we have. Most people sampled are between 24 and 34 years old. So it kind of has a like bell curve shape like that, I guess. But the fact that it is a bigger contributor does make a lot more sense. So this is a lot better for performance. So that's what I wanted to kind of go over in this one. So thank you for watching, and I will see you in the next one.